Okay, good afternoon, everyone. Let's get started. Can you hear me? Okay, great, thank you. So before the lecture, just a quick announcement. So the first programming assignment is due on 25th, I think it's Friday. So make sure you are submitting the report, the code on time. Okay, so we'll not allow late submission. Also, the second assignment is also released. So I've just opened this document here, and it is due March 24th. Okay, so for the second assignment, you will do the brain tumor segmentation using MRI. So just quickly go through, just give some background. So the data set we're using, this is a data set has been used for brain tumor image segmentation challenge. So this challenge has held many years. So it was co-located with a MICAI conference. Okay, so and the data set, the link for downloading the data set has been provided. So you can go through this link and download this task 1, brain tumor. Okay. So in this data set, there's 3 folders. If you unzip the file, there's a training images and test images, and also the labels for the training images. Okay, so the dataset JSON file, you can open that, and there's some details like what kind of modalities like T1, T2 flare of the brain MRI image, and what are the labels for different tumor types. Okay. So for this assignment, we are only using the training data because the test labels are not provided. So this is because this is a challenge, right? The organizer kind of hold the labels for the test image. So typically you will have to submit your prediction result of the test image, and the server will just calculate the result, like the dice scores and Hausdorff distance, and return that result to you. So, but to prevent some of the unexpected circumstances, we're not going to using the test images. Okay, just using the training images, and we will do the 5-fold cross validation. Okay, basically you partition the training data set into 5-fold equally, right? Then alternating each fold, right? Using each of the fold as the testing set, and generate the rest of for the training, and generate the prediction result for each of the fold. Okay, so for this one, this is my assignment. You have like 2 subtasks, right? First is just using this ITK software to visualize a few examples. So I want you guys to try these ITK snap software and visualize the data, right? And also the segmentation mask, okay? Because it's the label and the data has been provided. So just load a couple of examples using this software and visualize them, okay? So you can also get some, by visualizing these data samples, like what kind of tumors or classes are there for this MRI image, and what are they look like under different views, okay? And second, you will develop a brain tumor segmentation algorithm using UNet, okay? So we'll just keep it simple using the popular UNet. And you have the choice of choosing a 2D UNet or 3D UNet, okay? So we discussed in class, right? The 2D UNet is you process the MRI slice by slice, right? Treating each slice as a 2D image and apply these 2D UNet. You can also treat the entire volume as input and process that in a 3D fashion, right? Using 3D convolutional kernel by 3D UNet. Okay, so of course, the 3D UNet will be more computation expensive because of the 3D convolutional kernel, right? You have more parameters, more compute. So this, I give you the choice of using 2D and 3D, depending on how many computing resources you have, right? So you can, choosing between these 2. Of course, if you are interested to see the difference, for these 2D or 3D versions, you're welcome to try both, right? If you have the bandwidth to try both, you're welcome to do so, right? And do a comparison. So I think that'll be a great. So in the report, you will have to provide just a couple of one visualization example, and clearly indicating, all right, the implementation details of the network, right? The batch size, input size, learning rate, etc. Right? So that's the usual how to reproduce your result, right? Based on these kind of training details. And also have a table to list the result, right? So these are the result for the segmentation for the medical image, the dice score and the Hausdorff distance. And for each fold, right, because we're doing 5-fold cross-validation, so you can list the result for each of the fold and also provide the average of the 5-fold, okay? And lastly, you can also provide some visual examples, right? Just to do some qualitative analysis, right? Here I give you an example, right? So you can pick up a sample, then take maybe one slice of this sample, right? Show the ground truth. Also, on the side, you can put your prediction, the segmentation mask of this slice, and compare to the ground truth. Okay, so here, the segmentation mask and the original image are overlaid. Okay, so just to show, right, where that tumor has been located, right? So you can also using this ITK Snap software to visualize this, right? You can, input your prediction and visualize that and compare to the ground truth, okay? And generate this kind of visual comparison, okay? Okay, so, and also I also give you some of the example code. So just to get you started, right? How to load the data pre-process and, how to compute some of the loss and these generate those dice score, etc. So you can take those as example, okay? Any questions about the assignment? Okay, great. So then let's go to our lecture. So for today's lecture, we'll talk about federated learning. So maybe some of you, this is the first time you've heard of federated learning. That's totally fine. It's actually very easy to understand what's the high-level idea of federated learning. And we'll also talk about some applications in medical image computing. Okay. So we all familiar with this, the traditional centralized machine learning, right? How you train the model, right? So to harness the big data, right? We have all these IoT devices. So we want to harness the big data. So the centralized training way is all these devices will send the data to the cloud, right? So the cloud will collecting all the data, right? And train a machine learning model in the cloud, right? Based on these big data, right? Once the model is trained, then send the model back to each of the device. The users can use that trained machine learning model. Okay, so that's the centralized machine learning. So, so a lot of applications right now, right? If we are doing some like image classification, right? So we are still doing this centralized training paradigm, right? You have ImageNet data set, right? So you have all the data, you have the training set prepared, right? You train the data, then deploy that train the data. But there's several challenges for centralized machine learning. So first is the connectivity, right? So because we are, trying to harness the big data distributed on the distributed devices, right? The data has to be transmitted over a stable connection, right? We want to send the data to the cloud, right? So it kind of relies on a very stable connection, right? But for a lot of places, maybe in the developing country, right? So we don't have a stable connections. Then this could be a problem, right? You are not able to send your data to the cloud. And also the bandwidth, all right? So maybe some of the area, right, you don't have, 4G, right, even don't have 3G. So there's a limited, bandwidth to sending the data, right? Also, some of the locations or devices were able to generate a huge volume of data, right? So for example, this electrical substation could generate 5 gigabytes of data per second, right? So that's a huge amount of data, right? How can you send these huge amount of data to the cloud all the time, right? That also be limited by the bandwidth. Another challenge is the latency, right? So you have to send the data, then once the model trained on the cloud, right, then send the model back to the device, right? So there's gonna be some latency depending on how the model is being trained, also the connectivity, right? So if you have a slow speed or limited bandwidth, then you're gonna encounter some of the low late, high latencies. But for some of the applications, we require very low latency, right? So for example, you want to do some of the surveillance, right? Let's say you want to do license plate recognition, right? You definitely want to have a very low latency, right? You don't want to wait a couple of seconds, you generate a result. And also another very big issue is the privacy, right? Because all the clients or users will sending their data to the cloud, right? Oftentimes those data will contain some, privacy sensitive data, right? Like the name, gender, etc., right? So, or maybe some very private information. So in this case, if you're sending the data to the cloud, then the privacy might be an issue, might be compromised. Okay. Also, there's also a high demand on the storage and computing capacity of the server, right? Because the server is accepting all the data, a lot of data from the users, right? So you need a huge storage to store the data, and also needs to have a very large computing capacity to handle this large volume of data and to train the model, right? So that also create a huge burden on the server side. So to address this issue, right, then maybe one can easily think of how about we just, from centralized to decentralized data, right? We just, each of the clients or each party will just learn based on its own data, right? So for example, here, let's say I have a smart car or smartphone, right? So instead of sending the data to the cloud, to leverage or harness this kind of big data knowledge, I will just train the model based on the data I have on my local device, right? For some of the institutions like hospital, right, just relying on the data from my hospital, right? Don't using any of the data outside the hospital, right? Any other institution as well. Then we'll train the model on its own, right? But here also has some limitations by learning on its own data, right? One reason is the local data set may be very small, right? For example, the hospital, right? The data may be very scarce, right? Some of the rare, disease, you don't get a lot of data, right? So if you train the model based on the small data set, then the model performance can be compromised, right? Maybe due to the overfitting issue. And also there's a risk of the result is not statistically significant, right? Especially for some medical studies, right? You need a large population of the data sample so that your result has some statistical significance, right? But this will create an issue if you only have a small data set created on site. And also another limitation is the local data set might be biased, right? It may not represent the target distribution, right? Just as these figures depict here, right? Maybe your local data set will just have a distribution like this, but your actual distribution may look like this, right? So in this case, the local data set might be biased. And the federated learning is trying to address these issues, right? And the goal is we want to do collaborative training or learning, but at the same time, we want to keep the data decentralized, right? We don't want clients or users to share that data, but still we wanted to collaborate and learn from each other, right? So the knowledge can be shared, and then the model can be more robust or more generalized. Okay, so for this figure, this kind of depict the general setting of the federated learning, FL for short. You have a central server, okay? So you can think this is in the cloud, right? You have a central server, and also you have many local clients, right? So that could be like for ourselves, right? We're using smartphones, right? We can be, a user in this kind of federated learning, paradigm, okay? Each user or each local device will generate their own data, okay? But this data will only sit at the local device, will never send to the cloud, okay? So how do we collaborate learn in this case if we don't share the data, okay? So federated learning says, okay, let's just initialize the model, for the server and the local clients, okay? Here we are assuming each of the local client or device and the server share the same model. Of course, in the federated learning research, different devices can have heterogeneous networks, right? Different networks than the server, but we won't go to that complex cases. So let's just keep it simple. Let's assuming the server and the local device will have the same network architecture. Okay, just make example, if we're doing image classification, right? Let's say all the clients and the central server will have ResNet 18, right? That's the same model. Okay. And in the beginning, we'll just do the random initialization for the model, right? Both the server and the local client, okay? And then each of the local client will make an update using the local data set, okay? So you have the model and you randomly initialize that, right? Then based on the local data, right? So for client one, I'm going to make a model update, right? Train this model based my own data and make a model update. Okay, let's say I'm training one epoch, right? I made an update to my model. This client two also using its own data, right? Maybe totally different than client one. So they use its own data set and make a model training, right? Train one epoch and generate a model update. Okay, so this goes for all the clients. Okay, so once the local all the local model maybe trained from the epoch, right? Then the client will send the model update to the server. Okay, so instead of sending the data, right? Again, remember the federated learning, the local client won't share the data, right? So instead, the local client will share the model update. So basically, the model parameters. Okay, so I'll send my updated ResNet 18 model parameters to the server. Client two will send its ResNet 18 model parameters to global server based on their its own data set. Okay, so as you can see here, each of the model parameter are using different colors, right? To indicating there's some differences because of the data are different, right? Each client has their own data, so the model update can also be very different. So the server will receive n copies of the n model updates, right? The model parameters. If there's n clients participate in the federated learning, and the server will do the model aggregation, right? Once the server receive all these model updates, and in order to, do some, collaborative learning, right? So the server will just do the aggregation. So the simple aggregation will be just take the average of the model, right? Because every client has the same network architecture, right? Just different copies of the model parameters, and the server also have the same network architecture, right? So just take the average of the parameters, then you get like a global copy of the model, right? This is indicated as a global model. Okay, and this server will send this global model back to each of the client. Okay, so this global model actually aggregates all the knowledge or information, from all the distributed clients, right? Based due to the weights averaging or other type of model aggregation strategies. So each of the client will receive updated model, right? And then based on this updated model, and each local client can continue the local training, right? Then train the second based on this updated model, then train this model again using the local data, right? And the process can be iteratively repeated, right, to many rounds. Okay, so each federating training round is denoted by the local model train their model, local client train their model based on their data set, and sending the parameter to the server, and the server do the aggregation and send back the updated model. So that's called one federate training round. Okay, and if you do this again, then that's going to be the second and the third federate training round, until the model kind of converged, or some of the specific requirement has been meet, right? For example, I need the model to achieve accuracy maybe 90%, right? Once I see the model is able to achieve 90% accuracy, then I can stop, updating the model. So this will meet the requirement. So ultimately, for the federated learning, we would like the final model to be as good as the centralized solution, right? That's the ideal case, right? So the final model we want to achieve for the federated learning is just like you are training the model in the centralized way, right? You have all the data collected and you train the model in the centralized fashion. Or at least, if this is difficult to achieve, definitely there's, we will talk about later why this is difficult to achieve. But at least we should, this federated learning model should be better than, each party trained using their own data, right? Because the idea is that we want to involve this collaborative learning, right, from other clients, right, to harness some additional information to achieve better performance rather than train the model based on its own data. And there's also some key differences with distributed learning. Okay, so distributed learning, actually the data is centrally stored. Okay, so usually stored in the data center. Okay, so this data center may also have a very large, maybe computing cluster. Okay, the data is centrally stored. So the distributed learning is, the goal is to train faster, right? So you have all the data stored, and I have all these, computing resource, right? Maybe you have many GPUs, then I'll just distribute the data to different, all these workers in parallel, right? So that your model training can be, much faster. Okay. So usually the data was, distributed uniformly across all the workers in the data center. But for the federated learning, the data is naturally distributed and generated locally, right? So each of the client will generate its local data, right? Maybe the cell phone you have, right? The smartphone have you take pictures every day, right? The data is generated locally, okay? And it also distributed, right? Naturally distributed because of different users. So in this kind of scenario, the data in the federated learning usually is not independent and identical distributed. So it's non-IID. Ideally, we want to train any of the machine learning model, we want the data to be in the IID fashion, right? So you have the draw from the same distribution, they are not independent to each other, right? So your model can generalize well, right? So that's an assumption we in the supervised learning, right? We train the model on the training set. We assuming this is IID distribution, so we can using the trainer model test on the test data set, right? So it may generalize well if we have this IID assumption. But in the reality, right, especially in the federal learning, the data is very has very high level of non-IID-ness, okay, and also is imbalanced. And anyone can tell me like why in this case the data is non-IID distributed in federal learning?
For one, you have different devices that are taking in the data, and there's going to be subtle differences in those devices that are going to, even if two cameras take the same picture of the same scene, there's going to be differences because of that.
Yes, right.
Yeah, and also because it is imbalanced because at a hospital there won't be many cases of particular disease, whereas in another place it might be more cases.
Right, right. So just to give you a simple example, right? Say if we are considering, the smart cameras, has been installed in the city, right? In the city of Orlando, right? We see a lot of, those traffic cameras or surveillance cameras, right? On the traffic conjunctions or maybe public places. So let's assuming we are trying to learn maybe like a vehicle detection model, right? Using federated learning, right? Want to harness all these data distributed over the camera networks, right? So if you think about, for the cameras that is located at the traffic site, right? It will only capture like vehicles. I'm sorry, the application is to anomaly event detection, like anomaly, like a car accident or some of the other anomalies. Okay, so in this case, the cameras, like in the traffic conjunctions, they will just capture some of the anomalies, maybe car crash or some other accident, right? But for other cameras, maybe located in the convenience store, gas station, maybe you don't capture the traffic accident a lot, right? Mostly you will capture some like a burglary or illegal gathering or whatever, right? It is very difficult and maybe suddenly capture like the car accident. So you can see that this data distribution is very different. Not just the data, but also label can be very different, right? Maybe one client don't even have this particular label, right? Because this is just not will never account in this kind of under the scene. But for other client, maybe have a lot of such labels. So the data, the feature, and the label distribution will be very different, and also can be very imbalanced. So this caused some of the difficulties in terms of the optimization, while also causing some of the feature divergence issue in the federated learning. And for the federated learning, there's also some different types of federated learning. So here, just give you a very simple example. We have the cross-device federated learning, and also have this cross-silo federated learning. Okay, so for the cross-device federal learning, typically will have a massive number of parties, right? So in this scenario, one application could be we are trying to do some, federal learning over the smartphones, right? For example, we want to do, the text typing prediction, right? You're typing on your keyboard, right, to do some text messages, right? So actually Google can using federal learning to harness the data of millions or even more users of the smartphone and train a very good model to help you predict what you're gonna type in the next to complete the sentence, right? So you have a mass number of parties to participate in this federal training. And also each party will have a small data set, right? You don't generate a lot of data. Also, not all the clients are reliable, okay? So that means in the federal learning, any of the client can participate and also can drop out, maybe, drop at any point, right? Maybe I participate in the first training round and somehow, I close this app, right? Or maybe my battery, I don't have any battery, my phone is closed, right? So then this client will disappear or does not participate in the, federal training anymore, okay? And also, it is possible that some of the parties may be malicious, okay? So some of the parties can, engage a malicious attack, right? Maybe generate some of the, poison the data on this local model, right? Because of federal learning, you send the model to the server do the aggregation, right? So the malicious attack of data poisoning can affect the global model. Okay. For this cross-silo federal learning, it typically have much less, a smaller number of parties, right? Usually, 2 to 100 parties. And each of the party has medium to large data set. So usually the cross-silo federal learning is, between institutions, right? Hospitals, okay? And typically we won't have like, millions or even more hospitals to participate. Right, but each hospitals, more or less, they will generate medium or large size of data set, and they are reliable parties, right? It's gonna be rare, like one day this hospital decide to shut down, right? Do not operate. So more or less, the parties will be reliable, almost will always be available, for the federal learning. And parties are typically honest, right? Because they are institutions, there are some regulations to help them to prevent maybe some of the cyber attack, right? So they are mostly honest and trustworthy, okay? And federal learning is now a very hot topic, right? So the term of federal learning is first coined by Google researchers in 2016. And in 2020, there's more than 1,000 papers on federal learning. But now in the year of 2022, there's a much more than just 1,000 papers on federal learning. So a lot of researchers, they working on federal learning and working on different problems or sub-problems or subfield in the federal learning. Especially people working in the machine learning domain, right? They were trying to tackle some of the challenges in federal learning. And also people working on system, they are also working on the federal learning problem because they're also involving, right, the client and the server, right? How you are able to optimize the federal learning from the system level, right? So that's another field of people working on the system domain we're also working on this topic. And also people working in wireless communication, right? Or in communication in general, also have heavily devoted to federal learning because the convergence speed of your model also depending on the connectivity, right? If you're able to provide a very efficient communication, right, and the overall training process can be, facilitate a lot, right? The model convergence can be faster, okay? And we also see many real-world deployments by companies and researchers, right? So one example I said is the text completion or prediction, right? So you're typing those texts, by Google, and also a lot of like smartphones, right? Like speech recognition, Alexa, right, from Amazon. So they can also using federal learning, right? Each of the client, right, generate a lot of local data, and they want to train a better speech recognition algorithm, right? So they can using federal learning to constantly improve the model, right? And there's also many open source library under development or used extensively in industry and academia, right? So here are some of the open source libraries. So in particular, federal machine learning is the most recent one that used a lot in research. You can do some very quick prototype in PyTorch using FedML framework, okay? Like I mentioned, federal learning is highly multidisciplinary, right? It involves machine learning, optimization, privacy, cybersecurity, networking, system, and hardware, right? So this is a highly multidisciplinary research area. Okay, so next we'll look at a baseline algorithm just to help you understand, right, how federal learning is performed. So this algorithm is called Fed average. So it is proposed in this paper, Communication Efficient Learning of Deep Networks from Decentralized Data. So before we dive into the details of the algorithm, so first let's make some notations clear. So we consider a set of K parties or clients, right? So you have, K of them, right? Maybe mobile phones or some IoT devices, right? Each of consider one client, okay? And each of the client or party, right, will hold a local data set, DK, right, of NK points, okay? So each of the client will have their separate data set, DK, okay? And the D basically just the union of all the data, okay, from the K parties. And we want to solve the problem or minimize the empirical risk function, right? So if you're doing image classification and you can specify a loss function, right? Maybe you're using cross entropy loss, right? So each of the client will have their loss function, right? This is FK, okay? So based on their local data set DK, right? This data is the model parameter, okay? Everyone share the same model parameter, right? So the case client will have this loss objective, okay? And the global model the one to solve is we want to minimize the total loss, right? So from all the K parties. So for the Fed average, so this is the pseudocode of their algorithm, right? So let's first look at the server side. Okay, so on the left, so this is how the server is going to do the training. So the server also have a initialized model, right? So the parameter theta, okay? And let's say consider, T training round or capital T training round, okay? So then for each of the training round, right, the server will randomly select M clients. Like I mentioned, right, if we are doing cross-device federal learning, there's a chance that not all the clients are reliable, right? They may drop out at any time, okay? So this is to mimic that cross-device federal learning, right? You have a certain probability selecting a random set of clients, okay? So for simplicity, let's just assuming all the clients are reliable, right? All the clients going to participate in the federal learning. So you can think of this row equals to 1, okay? So we use all the K clients, okay? Just to keep it simple. Okay, so, and for each client K, so in parallel, right, each of the client will do their local update based on their local data, Okay, so here is the local update, right? Generate the model parameters theta k, okay? And once the theta k is generated from each of the client, right? They will send to the server, and the server will do the aggregation. Okay, so you have a summation and with this theta k. Okay, so there's a coefficient here, basically do some scaling, right? Based on the size of their local data, right? Nk indicating how many samples in this K, the local client K. N is the total number of samples from all the clients, right? So if you have a small local data, then your model maybe contribute a small portion, right? This is proportional to the local data size. Okay, so this is just a scaling factor, how you want to the model from each client to contribute to the global model theta. So for the local client, right, so we do the client update. Okay, so this is the step here, right? So how the local client do their update. So there was, this is nothing but just like the centralized training, right? Except they will train based on their own data. So you will have a batch size and also the number of local steps, right? How many training epochs you want to train based on your local data before you send in your model update, right? You can specify the local training steps, L, okay? So you also have this learning rate, right? If you do any of the gradient descent, you have the learning rate. And basically you just do the regular gradient descent, right? To update your parameters. And once you reach L step, right? Let's say you trained maybe 5 epochs, which you specified, then you are going to send in the local model to the server, right? For the aggregation, okay. So in their paper, one advantage or one contribution they make is trying to do multiple steps in the local training, right? Instead of just train a single step, in this case, L equals to 1, right? This is the equivalent to the classic parallel SGD. So they want to do not just one training step, maybe 5 or 10, just to make sure your model is able to achieve a certain level of accuracy before you sending that model update to the server. And they compare with this Fed SGD, right? Which means you only have to do once update on the local side. Fed average in their experiment setting, they do 5 times or training 5 epochs before you sending the model update to the server. And so this is the you can see this is like a convergence speed, right? So in the horizontal axis, this is the communication rounds or federated training round, right? We talked before, right? What is the federated training round, right? You train the local model, send it, do the aggregation on the server side, and you send it back. So that's called one federated training round. Ideally, you want to reduce the number of communication round, right? Because more communication round means slower convergence, right? You involve more communication, right? Data transmitting, right? The model parameter transmitting from the local to the server, server to the local model, local client. So when they do more training epochs on the local side, right? Let's say if I want to hit or one of the model to converge, right? Here, 80% test accuracy seems to be the accuracy the model is converged, right? And if you just do one time on the local training, you need about 3,000 or so, or maybe 2,500, communication round to make the model converge, right? But if they do this Fed average, right, you do more local training, is able to quickly make the model converge, right? Around 500 epochs, I mean, the training round, your model is converged to this 80% accuracy. So that's a significant like a speed up, right, for the model convergence. And as we mentioned before, right, so one challenge we have to deal with in the federated learning is the non-IID data, right? And because of this non-IID data, it will cause, a phenomenon called client drift, okay? So if we look at this figure here, okay, so you have this, the model, you have two models, okay? Client one model and the client two model, okay? Just to keep it simple, we have two clients, and you also have a server. Okay, we do the federated learning. And if we look at this client one, right? So based on their local data, and this is the model it kind of converged to. Okay, and if you look at client two, and this is the model. Client two converge to, okay. So these green, orange square, right? So that's the client optima, right? Based on their local data. So they are kind of converged to these kind of two local optima, okay. And in terms of the server, or the true optima, right? If you consider centralized training, right? So this is the true optima you want to achieve, okay? But actually, if you do this kind of aggregation, and the server model is actually converged here, right? So still there's some shift towards the true optima, right? So the reason is that each of the local client, right? So they optimized using their own local data, right? And because of this non-IID distribution, right? So they kind of diverge to different local optima on each of the client, right? So eventually, the client model often drifts away from the ideal global optimization point. Okay, so this will kind of create the difficulty of convergence, right? You need many federated learning communication round in order for your model to converge because of the client drift, okay? So to address this client drift issue, this method, FedProx, they propose a solution by adding a proximal term, okay, in their optimization function, and it's trying to limit the impact of the local update. Okay, so this is their optimization function. Actually, it's very simple. It's just adding this proximal term here. So this is the local loss function, right? You base your local data, right? You do this loss function, right? If you do the cross entropy, you have this loss function. Additionally, you also adding this proximal term. So this WT is the global or server model from the previous round, right? Let's say we are considering the local update, right? And this is the global model from the previous round. Okay, we are using T2 indicating that. Okay, to preventing your local model update, drift away too much from this global model WT here, it adds this proximate term, basically just the Euclidean distance, right, between the new model update and the previous global model weights, right? So this kind of penalize large drift towards this global model, right? If the new updated weights has significant difference than the previous global model WT, and this term will have a large penalty, right? You have incur a large loss, right? So in this way, kind of preventing the local update drift too much away from the global server. Okay, so that's their solution to kind of address this kind of drift issue. So learning from the ID data is difficult and slow because each party wants to model to go into a particular direction, right? So based on their local data, it has their own optimization objective or local optima. But if the data distribution are very different, learning a single model performs well for all parties, maybe require a very large number of parameters and maybe need a long, training time, right? You have many, federated learning training round. So another direction, to deal with this non-ID data, right? Rather, you can come up with some constraint, right? Like the Fed procs, right? To restrict the local update. Another direction is to, lift the requirement that the learner model should be the same for all parties, right? Like a one size fits all. Instead, we can allow each party to learn a personalized model, okay? Just to fit their objective, okay? So I'll give you a very simple example, right? How we can come up with a personalized model. So basically you can think of, each of a client, right? So let's say everyone have the same ResNet 18 model. Let's just using our previous example, okay? And the global model also using the same, right? ResNet 18. Right, here we want to do some customization, right? Because you have some non-ID data, right? If you want to enforce the same model for all the clients, may be difficult to fit their objective, right? How can we customize or personalize the model for each of the client? But at the same time, you also want to learn something that is shareable. So one way you can consider is you can maybe take partial of the ResNet 18, right? Maybe take, let's consider the width dimension, right? Maybe you take 80% of the model and using that as the shared model, right? And you can using the rest of the 20% as the like a personalizable model, right? You can, you learn different things based on the local model using that 20%, right? But the 80%, the rest of the 80%, you can share across all the clients, right? Do the global aggregation, right? Just to learn some shareable knowledge, right? But you can use the rest 20% to customize the knowledge towards your own data. So that's a way to do some personalized federated learning. Okay. So as we talk about, right, so federated learning do not, in the federated learning, client do not share the data to the server. But does this mean the data is safe? There's no privacy issue, right? So no third party is able to learn the, some of the, know the information of the local data. It's not the case. So actually in federated learning, there's also a challenge in preserving the privacy of the data, right? So that is the data leakage. The reason is that because the federated learning, we still share the model parameters, right? Some of the model update, right? Of the training process, right? If there is some malicious attacker, they can leverage these model update information to kind of do some engineering and reconstruct the original data. Okay, so there's still some privacy issues in federated learning. So let's see how maybe a malicious attacker is able to engage this kind of data leakage or data leakage attack. Okay, so this is the consider this federated learning, right? So you have this local client, right? You have the parameter server, right, to do the aggregation. Let's consider if the server trying to, peek into the local client data, right? The server had very curious, right? It wants to trying to reconstruct, what kind of data coming from the local client. Okay, so let's say this is a curious server. Okay, so how in this paper they have a way to do that, right? To achieve this data reconstruction just based on the model gradient or parameter. Okay. So the normal, this is the normal participant, right? So you have the data, right? You you do the local training, and you share the model update. And for some of the malicious attacker, right, the goal is trying to reconstruct some of the data of the local client, right? So the way the algorithm works is trying to match the gradient, okay? So because you have the access to the gradient, right? So what we can do is let's have a dummy input, right? Just randomly initialize some of the, just using some random noise, right? Because I don't know what's the original data, right? I just using some random noise. And because we know share the same model, right? We know the model, and we have access to the, the gradient. To do so, we can match the gradient, right? Let's say from this noise, for this model, I generate this gradient. I can match to the true gradient, right, and see how close my gradient from this noise as compared to the true gradient coming from the true data. Okay, then I can do this kind of optimization, trying to minimize the discrepancy, right? So I can using gradient descent, using this as the objective, trying to change my input such that at the end the discrepancy become very smaller, and hopefully that's the the actual data, right, resides on the local side. And this is the algorithm pseudocode from their deep leakage from gradient algorithm. So basically, they are trying to compute using the dummy input and the label, right, and compute the gradient and update the gradient, trying to match the true gradient they receive, right? This is like as we talk about in the adversary attack, right? So we want to add in some perturbation to the original image, and so that to kind of fool the model, to predict a totally different class label, right? To do so, remember we fix the model parameters, right? We do the usual gradient descent, right? Trying to optimize or trying to update the pixel value, right? Such that the label can be a totally different, not exactly as the ground truth, right? Or the prediction. So the same idea here, right? So we know the model and we have access to the gradient, so we can minimize the discrepancy of the predicted gradient and the true gradient and update the input, right? The input starting from the random noise. Eventually, if the model converges, and hopefully the updated image will reveal the true information of the data. So they do this kind of algorithm, and this is how they reconstruct the original data, right? You can see that this is the reconstruction result from different iterations, okay? So on the right side, these are the ground truths, right? This is the actual data from the client side. And this is the reconstruct images using their algorithm, right? Based on the gradient matching. So if we're doing enough iteration, right, you can see that the information can be correctly reconstructed, right? If we do some digit classification, right? So you can see that the original image pretty much like perfectly reconstructed, right? So this image and this digit and this person image also reconstructed, right? So
I have
this
a question.
Yeah.
So in this, they're only doing one image at a time. So they have the victim client is only processing one image and reporting the change in weights from that one image, right?
Yes.
So isn't this greatly mitigated by just having more samples in your whenever you update the weights, you would only
Yeah.
report
So
after several samples?
yeah. So in this case, you can actually reconstruct a batch, right? So if you have the gradient you can actually reconstruct a batch instead of just a single, right? You can consider, I want to minimize maybe a batch of image, right? The reconstruct the discrepancies. So you can actually also reconstruct like a large batch of image. So there's actually recent paper, they were able to using the gradient to reconstruct a batch of image at a time. So is that your question? Or maybe it's
Yeah, I mean, I get, yeah, that does answer it. Interesting. I'm curious about that other paper.
Yeah, so yeah, I didn't put it here, but I can, it's from NVIDIA. So it's a 2021 CVPR paper. So actually this is an early algorithm from 2019. So after that, there's a lot of this kind of inversion, gradient inversion attack, right? Basically you leverage the gradient, do this kind of inversion, right? Using the gradient to inverse that to reconstruct the original data. So there's a lot of like improved algorithm trying to reconstruct better data. So but yeah, I can share that data, the paper later. Okay. All right, so we have this attack. We definitely, want to have some defense mechanism, right? Because we don't want our model kind of exposed to all these kind of attacks, and we have this kind of data leakage issue. So there is some, common strategies can have this privacy preserving. So one is the homomorphic encryption. So you basically just doing some encryptions on the data, and also have the secure multi-party computation. So this is actually used by a lot of companies doing this secure multi-party computation, and also using the differential privacy. So I'm not going to go through the details of these different methods because they are very complicated. It's not the scope of this class, but these are some of the commonly used strategies that can, prevent this kind of data leakage, and has been used in a lot of real-world applications. When people do this kind of distributed or federated learning. Okay. So since we know some of the high-level idea of the federated learning, and it has been used in a lot of applications, right? So one big application is the smartphones, right? So on the smartphone, we have a lot of apps, right? You can do face detection, right? When you use the cameras, right? We can using some AI algorithm to do the face detection, right? We can do the word prediction when you type in the text messages, right? So federated learning can be used to harness or leverage these huge amount of data on the smartphone, right? Without leak the private information, right? As compared to you have to sending the data to the cloud. And also for the organization can also benefit from federated learning, right? Hospitals, in other institutions, without sharing the data, they are able to do some collaborative training, right? So then the model can be constantly or frequently improved or updated, right? This is especially good for like a manufacturing, right? So a lot of manufacturers, they cannot share their data, right? But if they are in the same or similar sectors, they definitely want to share some of the common knowledges, right? So to help them to improve, if they have some AI models, okay, maybe doing some like a defect detection, right, on their manufacturing lines, right? You want to constantly to improve the AI model, so it's able to cope with different defects or improve the model over the time. And also internet things, right? We are not just have smartphones, we have a lot of smart devices like smart watch, right? Autonomous vehicles, right? Smart sensors, right? So these devices also generate a lot of data, right? 24/7, right? So we can also using this data to train a machine learning model in a private preserving way, right? Without sharing the data, and also able to improve the user experience. Okay. So let's look at a couple of cases how federated learning is used for medical imaging. And the first case is a team of researchers, they using federated learning to train a model trying to predict the oxygen requirement of patients with COVID-19. Okay, so the study is led by the Mass General and NVIDIA. So they use data from 20 institutes across the globe to train a federated learning model called this exam, right? It stands for Electronic Medical Record Chest X-ray AI model. So the model is able to predict the future oxygen requirement of patients with COVID using the vital signs, laboratory data, and chest X-rays, right? So though in the COVID case, when 2019, 20, and with the surge of COVID, a lot of hospitals, is kind of they don't have those resources to to supply their patient, right? The ventilators, those things, right? They want to using AI to predict like the oxygen requirement for their patient, so they can maybe better allocate their limited resource, right? Given their priority, right? Maybe this patient need the oxygen immediately, right? They want to kind of do this kind of optimization. So they train this federated learning model using different institutes across the globe. So they are able to collect a lot of data from different hospitals and train this model without sharing the patient data, right? The patient data is very sensitive. Usually you cannot share the patient data, but you do want to have a large population of the data, right? To generate a model that can generalize well, right? To different cases, different demographies, different races, different genders, right? To generalize well. So that's one use case for the federated learning. And this is one figure, they report their result, right? So the blue bar is their model trained only based on their local data, right? So without, using federated learning, right? Have the knowledge from other hospital. This is the predictions for each of the client, right? Those 20 hospitals or participants, if they only train using their own local data, so this is the AUC they get for predicting this kind of oxygen requirement. But if you're using the federated learning, right, so they are able to improve the performance a lot across the board, right? Basically for every client or hospital, right, they are able to improve the performance. And the second one use case also is dealing with COVID-19. They are also using federated learning to train a machine learning model to detect the lung abnormality in CT scans. Okay. And they recruit 132 patients from 7 multinational centers and three internal hospitals from Hong Kong for training and testing, and a 4 external independent data set from China and Germany for validating model generalization. So this is their paradigm to train the federated learning model for this lung abnormality in CT, right? So they train the federated learning model using federated learning to get all these internal data, And they also do this external validation, right, from mainland China, and also validate their model on the in the hospital in Germany. So healthcare industries has readily adopting further learning, right? So here are some of the hospitals or institutions, they are using further learning for their healthcare or medical imaging studies. Okay, so they are using the NVIDIA further learning platform for doing medical imaging. And also pharmacies also using further learning. So here are some of the industries they are using further learning in their application. So finally, not just healthcare or medicine, right? So other type of industries can also benefit from better learning, right? So definitely, these patient researchers, healthcare providers can benefit from that, but also like manufacturers can also benefit from learning, as I mentioned before, right? So manufacturers typically cannot share their own data, but definitely the knowledge can be shared across the board, right? So to kind of improve the standard. Also, based on our daily life, right? The IoT devices has been constantly used, and more or less the IoT device has some of the AI capability, right? So we want to leverage the data generated on the edge device, and train this federal learning model that can constantly improve the quality and to improve the user experience. Okay. So here are some of the federal learning workshops and conference. So as you can see that it's a very popular topic now. So that's why a lot of researchers are trying to organize workshops on this kind of mainstream conference, trying to gather researchers from this field and discuss what are the state of the art and what are the future research directions. So also want to advertise one workshop I'm organizing for the CVPR 2022. We are doing federal learning for computer vision. So if you're interested, if you're interested, if you want to submit your work, if you're doing some federal learning already, you're welcome to submit to this workshop. And we also invite several, keynote speakers to speak about their research on different aspects of federal learning. So if you're interested, definitely this is a good venue to attend, to get to know what's the latest, what's the state of the art for federal learning and for computer vision applications. And also I found out there's a special issue on IEEE transaction medical image processing, medical imaging. So they are also have this special issue on federal learning for medical imaging. So I think that's a very encouraging, right? So this, prestigious journal, they also care about this latest trend, right? Using federal learning for medical imaging. So I think that's also a very good sign. Okay, so here are some of the reference. So if you are interested in to know more about federal learning, here are some of the surveys or some of the field guides in terms of different issues or challenges in federal learning and what are the state of the art. And so you can, take a look. And if you are interested doing some research in federal learning, right? So I also suggest you look at FedML. So this the new framework for doing federal learning. And this is a very good ecosystem. So they also have some, this platform can do federal learning for NLP, federal learning for computer vision, and federal learning for IoT. So they have implemented some of the common or standard benchmark algorithm. So you don't have to implement yourself, right? So you can basically just call using that algorithm and maybe just plug it or use it to your, in your own application. So this is a very good resource to look at. Okay. Okay, so that's it all for today. Any questions?
Professor?
Yes.
Actually, I'm really sorry. Couldn't attend the office hours to ask my question. It's not more of a question, but it's more of a request. Actually, Professor, I have very less knowledge of how to work with the data of medical especially medical images. It's my first time working with it. So for the assignment one, I'm having some trouble. Like I'm learning through different kind of tutorials and all. So I'm worried if I can like submit that within 25th.
Yeah, so I think you have to, I give you enough resource to, there's an example code, right? So the Kaggle, they have some code to help you start with, right? So you can learn from that.
But
And
yeah, yes, Professor. Sorry, please go ahead.
yeah, and it shouldn't be that difficult, right? So you basically just, they have the code already, like how you can load the data, right? Medical
Yes.
image, the first assignment is basically just regular image, right? Just 2D image. There's not difference like a 3D volume something, right? Just a regular natural image, like you just load the data and do the training. So I don't think there's any, much of the difficulty to do that.
Yes.
So
Yes.
yeah, I think you can try your best to definitely try to submit on time. Otherwise, I won't allow late submission.
Yes. Yes, Professor. I was just like requesting if can be like a day more, because then like there's bit relief and I can literally try my best, because I don't know, like I got overwhelmed by
Yeah,
it.
I
I don't know
mean,
why.
one day wouldn't do much, right? So if you really, I constantly remind you guys, right, what the deadline. So you should start early. That's what I'm constantly reminding you guys, right? Don't wait till the last month. I mean, last week or a couple of days. But at this point, I cannot make exception for you unless I receive enough requests for the postpone the deadline. Otherwise, we'll just stick
understandable,
current
Professor.
deadline. Okay. So
thank you so much for considering. Thank you so much. Yes, I will try my best to do it, Professor.
Okay.
Yep.
Regarding the assignment, just real quick, can you clarify what the second subtask is asking to do? I think I understand, but I just want to make sure.
Yeah, so basically you just using train from scratch or using the pre-trained model, right? So pre-trained model using, training from ImageNet. So instead of like random initialize the model.
Oh, okay. All right.
Yeah, you're using the pre-trained model and then do the fine tuning, right? As we discussed in the class, right? How you can train from scratch, or you can using transfer learning, right? Which using the pre-trained model. So yeah, I just wanted you guys to compare and see if there's any, difference.
Okay, great.
Yeah.
Just a quick confirmation, we can use to submit the code, we can just submit it using a Google Colab link, correct?
Yeah, yes,
okay.
you can. Yeah,
Okay.
that's okay. Yeah.
Okay.
No problem.
Just making sure.
Yeah. Okay.
I'm curious if you have any opinions on more decentralized federated learning. I did a quick search and I found a few papers, but like, is that something commonly talked about in the field? Is it something people don't seem to care about? Is it, do you think it has a lot of promise?
Yeah, so I think I'm not sure exactly what decentralized.
So basically, just that there's no asymmetry between clients. So you have like a server, a centralized server, and then you have clients. So essentially just having only clients.